Okay. Okay, so let's commence with today's class, and we're going to finish up on chapter 9 today by looking at this concept of reaction yield. So if you recall, we talked about stoichiometry and we did a couple of problems where we determined a couple of things about a particular reaction. Going back to this example here, let me make this full screen. Okay, going back to this example here, and we determined in this case how much of a particular product can be formed, all right? Now, the whole concept of yields, let me go back to this slide here. Okay, why is this thing not responding? Let me try this. Okay, so the whole concept of reaction yield is very important because what is often found is that when you actually perform reactions to produce a particular product, the amount of product you expect to get based on the amounts of reactants that you start off with and the calculations involved is usually, in most cases, less than what you expect to get, all right? So when you compared what you expect to get to what you actually get in terms of the product outcome, there's a disparity. So therefore, ideally, you'd expect to get 100% of the product that is based on the type of stoichiometric calculations that we were looking at. However, as we stated just now, many reactions fail to give 100% of the product that you expect to get. And there are several reasons why. The most common reasons are these two right here. You might have the possibility of side reactions taking place, and this is particularly true in the case of organic reactions, right? You can have more than one type of product being produced as a result of a particular reaction, and that can cut down on the amount of product you expect to get. Another possible reason is that there are many reactions that are reversible, which means that the product themselves can react to form the reactants. So that can also affect the amount of product you expect to get. So in this particular area, what we try to do is give an expression as to how successful a reaction is in terms of the amount of product that you get compared to the amount of product that you expect to get. So that leads us to two definitions right here. We have what is known as the theoretical yield, which is the calculated amount of product that can be obtained from a given amount of reactant. And then we have the actual yield, which is the amount of product that you actually obtain if you did the experiment, got your product, and you weighed, all right? So very often the actual yield would actually be less than the theoretical yield. And therefore the ratio between those two is called the percent yield, right? So basically the percent yield is the actual yield divided by the theoretical yield, multiplied, of course, by 100%, and that gives you the percent yield. And this is very often used as a measure of the success of the reaction, all right? So what you'll find in practice is that if you're doing a reaction and let's say you get somewhere about 80% or above, you're doing pretty good because most reactions are not that successful in terms of the percent yield. It's more common actually to get yields of, let's say, 50% or even below, all right? So that's basically what we're talking about here with respect to the percent yield. The percent yield is equal to the actual yield, which represents the amount of product that you would get if you actually did the experiment, divided by the theoretical yield, which is the amount of product you expect to get based on your stoichiometric calculation. So here is an example. Let me bring this down here so that you can see this question. It says silver bromide was prepared by reacting 200 grams of magnesium bromide with an adequate amount of silver nitrate. Calculate the percent yield if 375 grams of silver bromide was obtained from the reaction. Okay, so the way I would do this is, and I think we had the equation for this already. Okay, let me do this here. Let me get my pen and let me get the black color. Okay, so the equation, if I remember correctly, for this reaction is AgBr plus AGBR is a product. So let me erase this here. Oops. Okay, so one of the reactants is AgNO3, and the other product is magnesium bromide, MgBr2, and the products would be silver bromide and MgNO3 2, and to balance this, we're going to need a 2 here and a 2 here. Okay, so what the question is saying is that you're starting off with 200.0 grams of magnesium bromide. And basically what we need to find out is the amount of product you expect to get, which is the silver bromide, AgBr. All right, so we start off with the 200 grams, 200.0 grams of MgBr2. And we have to multiply that by a conversion factor, which allows us to convert from moles to grams, which means we need a molar mass. So I'm going to do my cheating here. And use my molar mass calculator. So okay, so the molar mass of magnesium bromide is 184.11. So let me write that down here, 184.11 grams of MgBr2. And then the next conversion factor would be the mole ratio between the magnesium bromide and the silver bromide. And as you can see, there's a 2 here, and there's understood to be a 1 here. So we're going to put 1 mole of MgBr2 down here, and 2 moles of AgBr up here. So far, this will cancel out with this will cancel out with this, leaving behind moles of silver bromide. And then the last step in this process here is to convert the moles of silver bromide to grams. So we have to multiply by the molar mass. So the molar mass of silver bromide, AgBr, is equal to 187.77 grams per mole. 187.77 grams of AgBr per mole. Okay, so let me do this calculation here. And please, as I said before, do these calculations along with me so that you can correct me if I'm doing something wrong. Times 187.77. Okay, so according to my calculations, this is equal to 408.0, round off to 4 sig figs. So this is 8.0 grams of AgBr. All right, so that's a mass of the silver bromide, the product, which would be the theoretical yield. Theoretical yield. All right, but what the question is asking for is the percent yield. So how do we get a percent yield? Well, we divide the actual yield, which is given here, the 375.0 grams, divided by the theoretical yield, which is 408.0 grams, times 100%. And that's how we get that. So it's 375.0 divided by 408.0 times 100%. And we round this off to 4 sig figs. So according to my calculations, this would be equal to 91.9 91.91%, which is very good as far as chemical reactions are concerned. 91.91% is very close to perfection, all right? So that's basically how that is done, all right? And this is a typical percent yield type problem, right? Pretty much most of the problems that you'll encounter will be something of this type. Okay, any questions about this particular example? Any questions? Okay, so that's pretty much it for this chapter, chapter 9. So we're going to move on now to chapter 10. And chapter 10 is dealing with the concept of energy, very important concept in chemistry and also in physics and also in biology. All right, so this is one of those topics that basically is covered in different ways in different disciplines. All right, so let's talk about energy. What is energy? Well, the definition of energy is the capacity to do work, all right? Which begs the question, what is work? Well, basically, work is said to be done whenever you have force applied to something and that something moves, right? So if I'm pushing something along like, let's say, a block of wood across my desk, then by virtue of the fact that I'm applying force to it and the block of wood moves, then energy is said to be, well, work is said to be done, and I'm expending energy in order to do the work, all right? So that's the definition of energy. And there are different types of energy. You have mechanical, chemical, electrical, heat, nuclear, and radiant energy. But in the main, energy can fall into two big categories. You have what is known as potential energy, which is the energy that an object has by virtue of its relative position. And then you have what is known as kinetic energy, which we'll talk about shortly. But just to say something more about potential energy, I wish there's a way I could get rid of this or move it aside. How can I do that? Let me see. Okay, I'm learning something new every day about manipulating this thing. Okay, so let's look at a situation where you have a ball and let's say the ball is at ground level. Then what will happen is that if you move the ball up against gravity, right? Remember, gravity is pulling down on the ball. Then you're expending energy by lifting the ball. So when the ball reaches a certain height, then the ball would gain a certain amount of what we call potential energy, all right? So at 20 feet, the ball will have a certain amount of energy, which is a potential energy. And then if you move it up to 50 feet, the potential energy increases. So the greater the energy will be related to how high the ball is lifted above the ground level, all right? So that's just one example of potential energy, right? It's the energy that the ball has by virtue of its position relative to ground level. Another way of looking at potential energy, it is stored energy, all right? And a good example of stored energy is the energy that is stored in gasoline, right? So therefore, gasoline is considered to be a source of potential energy. And the energy is released in the form of heat when the gasoline burns. And as a result, the products of the burning of gasoline will have a lower energy compared to the gasoline itself. So that's why it says here that the heat is released when the gasoline burns, and that is associated with a decrease in the potential energy. So therefore, the products of the burning of gasoline, which is basically carbon dioxide and water, the products will have less energy compared to the gasoline that makes it or that forms it, all right? Which is stated right here. New substances formed by burning will have less potential chemical energy compared to the gasoline and the oxygen that the gasoline reacts with when it burns, all right? Okay, so that's one form of energy. The other category of energy is kinetic energy. And by definition, the kinetic energy is the energy an object has by virtue of its motion. So anything that moves has kinetic energy associated with it. So it doesn't matter what it is. So for example, a flag waving in the wind, or a bouncing ball, or a running man, or somebody that's simply running, or a soccer player who's also running and kicking the ball. All these are examples of kinetic energy at work, okay? Now, let's talk about heat, right? Which is a form of energy, so to speak. The definition of heat is actually a bit more complex than that, but it's a form of energy. In fact, by definition, it's a form of energy that's associated with the motion of small particles of matter, right? So basically, if you have an object or something material, what you'll find is that it has a certain amount of energy corresponding to the motion of the different particles, the atoms, the molecules, the ions, etc. And basically, the more heat it has, the more energy the particles themselves will have. Now, it's very important that you make a distinction between heat and temperature. People tend to confuse these two terms as if they mean the same thing. Temperature means something different, even though it's related to heat, all right? And the definition of temperature is shown here. It is a measure of the intensity of heat or how hot or cold a substance is, all right? So please know the difference between these two definitions. In fact, we're going to illustrate the difference between those two, but before we get to that, let's talk about the units associated with heat energy. Now, the metric unit of heat is the joule unit, all right? Or the SI unit is the joule unit, okay? And there's another unit known as the calorie unit, which is a non-metric unit. And the relationship between these two units is given right here, right? 4.184 joules is equal to 1 calorie, all right? And the definition here comes as a result of certain properties displayed by water, which we'll get into shortly, all right? But this is just to show you the relationship between those two units. And the definition of the calorie unit actually is given right here. It is the amount of heat energy that will raise a temperature of 1 gram of water by 1 degree Celsius. So that's where the calorie unit comes in with respect to the properties displayed by water. 1 calorie represents the amount of energy that is needed to increase the temperature of 1 gram of water by 1 degree Celsius. Okay, so as I promised earlier, we're going to make a distinction between heat and temperature, going beyond just a definition and using a particular example. So just to remind ourselves of the definitions. Firstly, heat is the energy associated with the motion of small particles of matter, while temperature is a measure of how hot or cold or the intensity of the heat for a system, all right? Okay, so let's say we have two containers filled with water, one where the water is 100 grams and the other where the water is 200 grams, right? Now they're both at the same temperature, which is 20 degrees Celsius, all right? So they're both at the same temperature. Now let's say we heat these two containers, all right? And we apply different amounts of heat. In this case, we apply 4,184 joules of heat to the 100 grams of water, and we apply 8,368 joules of heat to the 200 grams of water. Now, if you compare these two, you'll notice that this amount of heat, the 8,368, is actually twice that of the 4,184 joules, right? So the amount of heat applied here is greater than the amount of heat applied in the case of the 100 grams of water. The result of increasing or adding the respective amounts of heat to the two different beakers of water will result in a temperature increase, which will be the same. So both of them will increase to the same temperature level, even though the amount of heat that is applied in each case is different. And that is because in both cases, well, in each case, the amount of heat required to raise the temperature of 100 grams of water to the same extent would be double the amount of heat required to raise 200 grams of water, all right? So I hope this explains why, or the difference, I should say, between heat and temperature, all right? It turns out that the amount of heat required to raise the temperature of a given amount of a substance, in this case, water, would be greater if you try to do the same thing with a greater amount of the same substance, all right? So as stated here, twice as much heat energy is required to raise 200 grams of water by 10 degrees compared to 100 grams of water, which is what I said before, right? So I hope this explains and I hope you understand the difference between heat and energy based on what we were discussing here. Okay, so let me introduce to you now a particular concept known as a specific heat. Very important. It is actually a physical constant, all right, or physical property that different substances will have. So this is the definition of specific heat. The specific heat of a substance is the amount of heat required to change the temperature of 1 gram of that substance by 1 degree Celsius. All right, so that's a definition of specific heat. All right, and different substances will have different values for the specific heat. Now, let me first point out that the units of specific heat is based on the units that you would use for heat to make that calculation. So if you're using joules, then the unit of specific heat would be joules divided by grams degrees Celsius. If, on the other hand, the unit of heat being used is calories, then the specific heat units would be calories divided by gram degrees Celsius. So whichever units you're going to use is based on the particular or specific units of heat that is involved to make that calculation. So as you can see here, we have different values here. And you'll notice that of these substances here, water has the highest specific heat of all the substances that are listed here. And there's a reason for that, and that is due to a phenomenon known as hydrogen bonding, which we will discuss much later on in this course, all right? So that's a reason why water has such a high specific heat compared to other substances. Another thing I want to point out to you is that typically metals tend to have low specific heats, right? So as you can see here, aluminum has a specific heat of 0.900, iron 0.473, copper is 0.385, and so on and so forth. So metals tend to have a low specific heat, which basically means that it takes a relatively small amount of heat energy to raise the temperature of 1 gram of a metal by 1 degree Celsius. Whereas in the case of water, more heat is needed to raise the temperature of 1 gram of water by 1 degree Celsius. Okay, so with that said, as I said before, the units of specific heat, if the joule unit is used, would be this right here, right? This combination of units, joules divided by grams times degrees Celsius. Or another way of just writing the units using the symbols is this way, all right? On the other hand, if you're using calories, then this would be the combination of units, or you can simply write it this way, all right? So again, it depends on the units that you're going to use for representing the heat part of this arrangement right here. And in terms of the relationship between the mass, the temperature, the specific heat and the amount of heat, it is given by this equation right here. Now, Q represents the amount of heat lost or gained. M is the mass, which is usually expressed in grams. C is the specific heat, and delta T would represent the change in temperature, all right? So that's basically the equation right here. And let me just say something here. Let me go to my pen again. Oops. Okay, so usually Q would be in joules, but it can also be in calories. M would be in grams, and delta T can be in Kelvin or degrees Celsius. In which case, as far as C is concerned, depending on the units that you're using, C can be expressed in either joules per grams Kelvin or joules per gram degrees Celsius, or calories per gram degrees Celsius, or calories per gram Kelvin. So it all depends on what units you're using. Now, let me just say this. If the units are in Kelvin or degrees Celsius, it doesn't make a difference, all right? in terms of delta T, because delta T is going to be the same numerically, regardless of whether or not the temperature is expressed in Kelvin or degrees Celsius, all right? So numerically speaking, the units of delta T can be equal to K or degrees Celsius, Kelvin or degrees Celsius, but it won't change the value of anything else. It won't change the value of C for sure, all right? So that's just something you need to be aware of. And we're going to look at some examples using this particular equation. Okay, any questions so far? Any questions? Let me see if I can, okay, I may have, oh, okay, no questions. So let me go back to, okay, so, okay, why is this thing not responding? Let me go out of this here. Okay, so let's look at this example right here. So this question says you have to calculate the specific heat of a solid in joules per gram degree Celsius and in calories per gram degree Celsius if 1,638 joules raise the temperature of 125 grams of a solid from 25 degrees Celsius to 52.6 degrees Celsius. Okay, so the equation we're going to use, let me go back to my pointer, to my pen. Okay, so the equation we're going to use is, of course, what I showed you before, which is Q is equal to M times C times delta T, all right? So that means that C, which is what the question is asking for, would be equal to Q divided by M times delta T. So basically, we're just doing some rearrangement, algebraic rearrangement to solve for what the question is asking for. And then all we have to do from here is plug the numbers in based on the information provided in the question. The question gave us Q, which is 1638 joules, which is the amount of heat, divided by the mass, which is equal to 125 grams, times delta T, which is the change in temperature. So it's 52.6 degrees Celsius minus 25.0 degrees Celsius. All right, so that's basically the setup. So what I would do first is work out what's within the parentheses here. So that's 52.6 minus 25.0. And according to my calculations, this part here, oops, works out to be equal to 27.6 degrees Celsius. And then we do the rest, 1638 divided by 125 divided by 27.6. And according to my calculations, this works out to be equal to, and we need to run this off to 3 sig figs. So this works out to be equal to 0.475. And the units for this would be joules over gram degrees Celsius. Now, we're not finished yet because this question is also asking us to convert this to calories per gram degree Celsius. So what I'm going to do is start off with this down here, 0.475 joules over gram degree Celsius. And I will multiply this by a conversion factor, which allows you to convert from joules to calories. So the calorie unit will be up here. The joule unit will be down here. And according to what the question is saying, or according to the relationship between the two, 1 calorie is equal to 4.184 joules. So the joule units will cancel out here and here. And let's do that calculation. So all we have to do is divide 0.475 by 4.184. And according to my calculation, this works out to be equal to, again, rounded out to 3 sig figs. So this will be 0.114. And the units will be calories over gram degrees Celsius. And that is how we do that conversion from joules per gram degree Celsius to calories per gram degree Celsius. Okay, any questions about this particular example? Any questions? Any questions? Okay, so let's move on. I think I have another example coming up. Again, this thing is not cooperating with me. Okay, so before we get to the next example, let's talk about this concept, principle of conservation of energy. In fact, it's a law, right? And this law says that energy can neither be created nor destroyed, though it can be transformed from one form to another form of energy. Another way of stating this is that the energy of the universe is constant, all right? So basically, what this is saying is that you can have the transfer of energy from one form to another and from one object to another, but you won't have energy being created or destroyed in any process whatsoever. So this brings us now to example 2. Now, this one is a bit wordy, admittedly, but this is based on not only what we learned with respect to specific heat, but what we just learned with respect to conservation of energy. So this question says, a sample of metal with a mass of 212 grams is heated to 125.0 degrees and then dropped into 375 grams of water at 24.0 degrees Celsius. So the question says, if the final temperature of the water is 34.2 degrees Celsius, what is the specific heat of the metal? All right. Now, based on the conservation of energy law, heat cannot be created nor destroyed. All right. Now, before we get to that, let's think about what's happening here. We have a metal that has been heated to 125 degrees Celsius, and then it is added to the water, which is at a temperature of 24.0 degrees Celsius. All right. So what's going to happen, and I'm quite sure we are all aware of this based on our everyday experiences. What's going to happen is that you're going to have the heat flow from the hotter metal, which is 125, to the cooler water, which is at 24.0 degrees Celsius. All right. So basically what that means is that the amount of heat that is lost by the metal will be equal to the amount of heat that is gained by the water. As a result, the temperature of the metal is going to fall from 125, and the temperature of the water is going to rise from 24 degrees until you get to a temperature in between those two. And according to the question, that temperature is equal to 34.2 degrees Celsius. All right. So I'm just giving you a brief overview of what is happening here in this particular situation. So based on that information, the question is asking for you to calculate the specific heat of the metal. So the first thing I would do is write down a relationship between the amount of heat that is lost by the metal and the amount of heat that is gained by the water. And that relationship will be Q of the metal, I'm just going to put QM for the metal, will be equal to QW for the water, right? So this is the amount of heat that is lost by the metal, heat loss, and QW would represent the amount of heat gained, all right? So what I'm going to do now is write down specific expressions for the Q of the metal and Q of the water. So as far as the metal is concerned, that would be equal to the mass of the metal times the specific heat of the metal times the change in temperature of the metal. And that would be equal to, on the right side, the mass of the water times the specific heat of the water times the change in temperature of the water, all right? Now, what the question is asking for is this right here. The question is asking for the specific heat of the metal. So again, we have to do some algebra to isolate this on the left side. And you should know from your previous math experience is that to get rid of this and this, we have to divide both sides by the mass of the metal and delta Tm, mass of the metal times delta Tm. So these two will cancel out. These two will cancel out. So you're left with the specific heat of the metal being equal to all of this here. So Cm will be equal to all of this right here. So the trick now, and this is where you have to be very careful, is to plug in the appropriate numbers for these terms in this equation. So we have to look at the question and first identify in the question what's the mass of the water. And according to the question, the mass of the water is equal to 375 grams times the specific heat of the water. Now that would have to be given to you. And in fact, that is actually given to you in the tables that I've posted in Canvas. It's going to be 4.18 joules per gram degree Celsius times the change in temperature of the water. Now, what's the change in temperature of the water? It's going to be equal to, in fact, let me use a different color here so I can point it out. Let me use red. Let me use this color here. Okay. So the change in temperature of the water would be the difference between the 34.2 and the 24.0 here. All right. So down here, we're going to have times 34.2 degrees Celsius minus 24.0 degrees Celsius. All right. And then that would be divided by the mass of the metal, which according to the question is 212 grams, times the change in temperature of the metal. Now, what's the change in temperature of the metal? Well, remember, the final temperature of the metal will be the same as the final temperature of the water. So therefore, the change in temperature of the metal would be equal to the difference between 125.0 degrees and the 34.2 degrees. So therefore, here we're going to have 125.0 degrees Celsius minus 34.2 degrees Celsius. And from here, it's all a matter of doing the math. Of course, you'll work out what's in the parentheses first. So let me do that. 34.2 minus 24.0. So according to my calculations, this part here, okay, what's going on here? Where is it? This part here is equal to 10.2 degrees Celsius. And then for 125.0 minus 34.2, that part is going to be equal to 90.8 degrees Celsius. And then we have to do the rest. So 375 times 4.18 times 10.2 divided by 2112 times 90.8. So according to my calculation, this works out to be equal to, let me do this down here. Okay, I have to round this out to 366, so it's going to be 0.831. And the units, well, we can derive the units because the grams are going to cancel out here and here. Degrees Celsius is going to cancel out here and here. So you'll be left with joules divided by gram degree Celsius. So joules divided by gram degree Celsius. And that's basically how that is done. So the correct answer is this right here. All right. Okay, any questions about this example? Any questions? Let me check the chat. Oh, okay, somebody. How come you didn't multiply the 27.6 by the 125? Okay, what are you referring to? That was from the last question. Oh, okay, let me see what you're referring to. From the previous question you're saying. Okay, let's see. Okay, what's going on here? Okay, let me get out of this here. Okay, so I take it you're talking about this example, right? Okay, so you're saying multiply the 27.6 by the 125. I thought I did that. But okay, let me do it again. But I thought I did that. 1638 divided by 125 times 27.6. Yes, I did that. That's why I got the answer as a 4. Yeah, yes, that could be, it's possible that you could have done something incorrect. And this underscores a very important point. You guys have to be very familiar with your calculators and know how to use them properly, because in the past, one of the things that I've noticed is that some students basically don't know how to use their calculators and they end up with their answers being wrong. And I can tell that they have some issue with the calculator usage because they pretty much do everything right in terms of setting up the problem. But when they enter the numbers in their calculator, they do something wrong. I don't know exactly what. And therefore, as a result, they get the wrong answer, even though the setup is correct. So it's very important that you know how to use your calculator to do problems of this type. All right. Okay, any other questions concerning this or the other example? Oh, okay, good, very good. Okay, very good. Who is this person? I didn't even see the person's name. Oh, Mr. Pinsky. Okay, very good. All right, so if there are no other questions, let's see. Okay, what's going on here? We talked about conservation of energy. We did this example. Okay, so let's talk about energy changes in chemical reactions. So let me get out of this. Oops, what did I do? Okay, so let's talk about energy in chemical reaction, energy changes in chemical reactions. So in all chemical changes, then you must have some change also with respect to energy. So in some cases, you have energy being absorbed or energy being released, all right? And these are examples of energy being produced as a result of some chemical reaction that takes place. So for example, you can have electrical energy being produced as a result of chemical reaction taking place in storage batteries. So if you look at any battery of any kind, it doesn't matter what kind, it could be the ones that you use in your digital devices, or the car battery that, that is in your under the hood. Basically, the general principle involved is basically exploiting or harnessing chemical energy that is produced in those batteries, in those devices, so that they can, be used to perform a particular function, produce electricity, which will produce light and all of that. So that's one example. Another example is a light stick, which is using, again, a series of reactions basically to produce light. And then one that is very common that I'm quite sure we can relate to, the combustion of fuels, right? So it doesn't matter what the fuel is. It could be methane, it could be gasoline, it could be propane. Again, what happens is that you have a chemical reaction, in this case, the burning, where the reaction is between these substances and oxygen in the air. And these typically produce heat and light. Oh, yes, ma'am.
You stopped sharing your screen. We can't see it.
Oh, I did? Oh,
yeah.
Sorry about that. No, how did that happen? I'm so sorry. I didn't realize that I stopped sharing. Okay, I take it you can see my screen now, right?
Yeah, I can see it.
Okay, good. Sorry about that, folks. Still, believe it or not, learning about how to use this. Okay. So this is what I was talking about. This table gives you some examples of different situations, devices where energy is produced as a result of chemical reactions. I talked about storage batteries. I talked about a light stick, which uses a series of chemical reactions to produce light. I talked about the fact that burning of fuels, propane, gasoline, whatever, that produces heat and light as a result of the combustion of these fuels. And then the final example here is what our very lives depend on. Different chemical reactions occurring within the cells of our body, which produces energy so that we can basically live and move and, whatever. All right. So these are all examples of energy being produced as a result of chemical reactions taking place. All right. So this is the light stick that I referred to earlier. And this basically produces heat energy as a result of this series of reactions. Now, this may seem confusing to you because I don't think any of you have been exposed to organic chemistry, but basically what is happening is that this molecule here reacts with hydrogen peroxide to form these two molecules. This molecule here is very unstable, right? And therefore, because it's very unstable, it has a high amount of energy associated with it. So much so that when it reacts with a dye, it basically transfers energy to the dye, and the dye itself becomes energetic, and carbon dioxide is the byproduct of that step. And then that dye produces light almost immediately. That's what HV here represents, light. I won't go into the details as to why that is used, but that's basically what happens. So this is just showing you the series of reactions that is responsible for the light that is produced in the light stick here. Okay, then there are other reactions where, there are certain reactions where energy is absorbed in order to cause these reactions. So a good example of this is the electroplating of metals or the decomposition of water into hydrogen and oxygen, all right? So in both of these cases, what we're using is electrical energy to make these reactions occur, all right? And then another example, which occurs in nature, of light energy being used to drive chemical reactions is the photosynthesis that occurs in green plants. As you all may know from your biology courses, green plants have a substance in their leaves known as chlorophyll, and that substance is able to trap light energy from the sun, which allows for a series of reactions where carbon dioxide and water is ultimately converted to glucose, all right? So these are all examples of chemical reactions taking place as a result of light energy being used to drive these reactions. Okay, and let's look at what happens actually when a chemical reaction takes place and the type of energy transformation occurs. Now, this is a very simplified explanation. It's actually a bit more complex. In fact, if you plan to do Chem 2, then you're going to learn more about these sort of energy changes. All right. So if energy is absorbed during a chemical change, then what will happen is that the products will have more chemical potential energy than the reactants. And there's actually a name given to this type of reaction. And let me write that name down here. It's called an endothermic reaction. Endothermic reaction. All right. So a reaction where energy is absorbed as a result, the products will have more energy than the reactants. We say that that reaction is endothermic, which basically means that it absorbs heat. And then the opposite of endothermic is exothermic, where energy is given off, and as a result, the products will have less energy compared to the reactants. So we call this an exothermic reaction. All right. Okay. So that's the difference between these two. In the case of an endothermic reaction, energy is absorbed, usually in the form of heat, and therefore the products will have higher or a greater amount of energy compared to the reactants. And then we have the exothermic reaction, which is basically the opposite, all right? Where the products will have less energy compared to the reactants, and that's because there's an energy loss as you go from the reactants to the product. So this diagram here, and again, this is an oversimplification of what actually happens, but this diagram here basically illustrates the difference between these two. Now, in this case, we're looking at the reaction between, let me write this down here. We're looking at the reaction between hydrogen and oxygen to form water. So this is the equation for the reaction. All right. Now, specifically, this, oh, I need a 2 here. Specifically, this is associated with this diagram right here. So basically, you have the hydrogen combining with the oxygen to form water. And you'll notice, well, let me explain what's happening here. Let me go back to my pointer. So what's happening here is that the hydrogen, well, this x-axis here represents potential energy, and the y-axis represents time. So basically what you'll notice is that the hydrogen and oxygen will have a higher energy compared to the water, right? So basically, as the hydrogen and oxygen are converted to water, there'll be a corresponding loss in energy, right? So that's what happens when you burn hydrogen in air. So therefore, this is representing the exothermic process. So let me write this down here. So, okay, this is exothermic. All right. Now, if you look at the reverse reaction going the other way, then the corresponding diagram would be this diagram right here. And in this case here, you're starting off with the water here, which would have a lower energy, right? And it's converted to hydrogen and oxygen, which is of a higher energy, right? And that's what happens when you pass an electric current through water. So this process here is endothermic. Let me write this down here, endothermic. All right? So that's the difference between an exothermic and an endothermic reaction. And one thing I must say here, which is true for every reaction, if you go in one direction where the reaction is exothermic, then going in the opposite direction, the reaction is going to be endothermic, right? It doesn't matter what the reaction is. And that is plainly seen in this example, right? So if you're forming water, then that process will be exothermic if you're forming water from hydrogen and oxygen. But if you're going the opposite direction, if water is reacting to form hydrogen and oxygen, then that process is going to be endothermic, right? So for one direction, the reaction will be exothermic, and then for the reverse reaction, it's going to be endothermic. Okay, so that is just showing you that in the case of the first reaction, energy is absorbed, and in the second reaction, energy is given off. Okay, so believe it or not, that represents the end of this chapter here. Let me see here. Okay, so that's the end of chapter 10. And what that means, therefore, let me go to the Canvas shell. Okay. Let me get this out of the way. Okay, let me go to 10:25:03. Files, and then assignments. Okay, so let's see here. Let me see what chapter 8 assignments. Okay. I'm trying to remember, did I give you these assignments? Let me see here. Okay, I gave you assignment 15, apparently. Okay, so basically, assignment 16, 17, let me see here. 18, 19. Okay, and then I'm going to publish this here. Okay, and then assignment 20. Okay, now this is what I'm going to do, because since you have a test to do next week, I'm going to unpublish that one. I'm not going to give you these assignments quite yet, because I think you need some time to prepare for your upcoming test. But I'm going to leave them open, or I should say leave them published, so that you guys can look at it if you want to. I'll probably give you a deadline date of sometime next week to complete those, because right now, as it is, I think we're kind of ahead of schedule in terms of the topics covered. But just to remind you that the test that you'll be doing next week will cover chapters 1 through 4. All right. So make sure that which reminds me, I keep forgetting. Now, I have emailed most of you back your assignments that I've graded for you. But there are a couple of you that have not been able to do that, because the main reason is that for some of you, when you submitted your assignments, you did not write your name on it, right? And as a result, even though I may have graded it, I don't know who it belongs to, all right? So for those of you who may not have received back your graded work, more than likely that's a reason why you have not received it. So for such persons, please resend or resubmit your assignment, but this time, please put your name on each sheet of paper that you resubmit, so that I can properly give you the credit for your work. All right? So please do that as soon as possible, so that I can grade it and then send it back to you. Another thing I want to say, I think I have published all the assignment keys for, let me just check and make sure. Yes, I did. All the assignment, let me just check here, chapter 4. Yes, okay. So I have posted all the assignment keys for chapters 1 through 4, which corresponds to assignments 1 through 7. All right, so you have that to review. I would strongly recommend that you review those problems. And I would also strongly recommend that you check out the textbook and do problems from the textbook itself, right? Because the more practice you get, you get in terms of problem solving, exercise, and so on, the better you become at doing that, and the more likely you do well in your test. All right. So that's pretty much all I have for today, unless there are any questions you guys have. Any questions? Oh, okay. Somebody just said, oh, yes, right. I agree with you. Yes, like I said, I won't pressure you to do the others quite yet, since you have a test coming up. And that's in response to what Terence Stepinski is saying. Okay. Any other questions or comments? Or please remember also to call ahead and make an appointment at the testing center of your choice. You can go to any one of the testing centers of any of the campuses, the one that's most convenient for you. All right. So that's basically all I have to say. So if there are no other questions, enjoy the rest of your day, and I'll see you guys here on Wednesday. All right. So take care. Have a good day.